and welcome to this third talk in the Informs Tutorials in Operations Research series. We're very excited to have a tutorial that talks of the connections between artificial intelligence and simulation optimization. My name is Hari Balasubramanian. I'm one of the co-editors of the tutorial series this year, the volume this year. I'm co-editing it along with Professor Ebrubish. We also have the series editor, Dr. Douglas Shear, who is here with us. So I think we were going to do the introductions first. So I'm going to do the introductions of the speakers first. As I said, it's a tutorial that talks of the deep connections between simulation optimization and artificial intelligence. We have three speakers today, and I'm going to introduce all the three speakers. Professor Yiji Peng is an associate professor in the Department of Management Science and Information Systems in the Guanghua School of Management at Peking University. He has published in many papers in Informs journals, Operations Research, Informs Journal of Computing, as well as IEEE journals such as IEEE Transactions on Automatic Control. He won the 2019 Outstanding Simulation Publication Award at the Informs Simulation Society. And it's the Informs Simulation Society that nominated this talk, and so I'd like to thank the society as well, the Informed Simulation Society as well. His research interests include stochastic modeling and analysis, simulation optimization, machine learning, and healthcare. We also have two other co-authors, two other co-authors and presenters. Professor Chin Hong Chen is a professor at the Department of Systems Engineering and Operations Research at George Mason University. His research has been funded by National Science Foundation, National Institutes of Health, Department of Energy, NASA, and many others. And he has been developing very efficient methodology for simulation-based decision-making and its applications. Dr. Chen is an author of the popular book, Stochastic Simulation Optimization, an optimal computing budget allocation. He's also a fellow of IEEE. The third co-author of this talk and also a presenter is Professor Michael Fu. Professor Fu holds the Smith Chair of Management Science at the Robert H. Smith School of Business with a joint appointment with the Institute for Systems Research at the School of Engineering at the University of Maryland. He's a fellow of IEEE and Informs. He was the program director of the Operations Research Program at the National Science Foundation from 2010 to 2012, as well as 2015. And he was also a general co-chair for the 2020 Informs National Meeting. And I know that how much work that is involved for the community, so thank you very much for being a co-chair at that time. With those introductions, I think we can proceed with the talk. Yeah.
Good afternoon, everyone. Thanks for coming, and thanks for organizer inviting us and for the introduction. My name is Chin Hong Chen. Welcome to our tutorial. Actually, the order of the name actually is the presentation order, not the order of the authors. So EJ is really the first author. And as we know, many of the OR methodology have played important role in the development of the AI. So a particular simulation optimization is pretty critical in some of the AI development. So in this tutorial, we are going to give a presentation about give an overview of some critical simulation optimization methodologies, and we'll bring the connection between the methodology and the AI development. So I'm going to turn this over to my co-author, Professor Michael Fu. Michael.
Thanks, Jun Hong, and thanks also to Doug and the chair and his co-editor. We're very happy to present this work. So I'm going to talk for about 1/4 of the time, the remaining time, and then EJ will be talking for most of the remaining time. I'm going to begin by trying to, let's see, to try to give a big picture view of what the topics that EJ will be covering. So I start with one example that's well known in the OR community, multi-echelon inventory management. So below is kind of a schematic of a simple sort of 2-echelon, well, depends on how you count. If you want to count the manufacturing customer, it could be 4, but let's think mostly 2-echelon level warehouse network. And as we all know, decisions have to be done of how much to stock at each of the different warehouses there, right? So that's a typical OR problem. The figure on the right is actually something EJ, I think's worked with JD.com in China. So he's going to talk more about this specific problem later in his portion, but I'm just using this to try to motivate this. So as I said, sort of traditional OR optimization is something like, for example, choosing order amounts or choosing the setting the base stock levels, you know, at each of the warehouses. What I would call old, and that's in quotes, simulation optimization method is that you might have a big simulation of this entire network, right? And then you might even have some sort of math program out there that tries to set sort of basic preliminary base stock levels, and then you simulate this, and then you might use something like stochastic gradient search to improve, for example, the base stock levels. Okay, so that's kind of what we feel as the old simulation optimization method. What I call the new era of AI, a paradigm shift, is that we all know about Markov decision processes. You could go back to modeling these inventory control systems as a Markov decision process, and the theory of the stochastic modeling was what gave you, the ways to calculate some of these things very efficiently, like the base stock levels. But theoretically, if this is a complicated multi-echelon, multi-period system, then you may not have base stock levels that are sort of constant over time. They may vary over each period, because demand changes and so forth. And so you may actually need a full Markov decision process model to solve it, kind of more accurately. But nobody did that before because was just computationally impractical. Okay, so now instead what we can do is we can go back, we say, well, we're going to go actually back to MDP and solve this using deep reinforcement learning. And what we're going to actually do is, instead of doing sort of a static optimization level optimization problem, we will actually try to do what I call a full detailed action policy. So this would give you what to do for every possible state, what action to take in every possible state, and usually it would actually be a probability distribution over the action space. So now, instead of doing search on the original decision variables, such as the base stock levels, you're actually going to do stochastic gradient search on a policy parameterization. So this action policy, this distribution over actions, will be parameterized by some parameter, and that becomes your decision variable. And then, so this parameterization, for example, most of this talk will be neural networks, and the parameters will be things like the synaptic weights in the neural network. So now your optimization will be with respect to those instead of the base stock levels. So that's kind of a big picture of the general idea of this sort of paradigm shift. So since this is a tutorial, I'm not going to assume everyone knows what a stochastic gradient is. So let me just kind of give a quick intuitive definition, and then we'll get into a little bit more of the technical details soon. So just think of a stochastic gradient as a sensitivity of a random output to input parameters, as opposed to a deterministic function. So examples in traditional OR, like the inventory system I talked about earlier, the inventory costs with respect to, say, the reorder point or even sort of a distributional parameter like mean demand. So what you do is you simulate the system, and then you get an estimate of the gradient from that simulation. And the actual thing you're trying to estimate is usually a sensitivity with respect to either an expectation or a quantile, or even a possibility of the entire distribution. So the analog in the traditional AI or machine learning setting is that you have a loss function with respect to the ANN, artificial neural network training parameters, like I talked about in the previous slide, like the synaptic weights. And then here you are sampling, for example, from a real system. You have this big data set, and you're not going to try to calculate the loss function for the whole data set. So you sample part of it, and then you calculate the stochastic gradient. It's a stochastic gradient because you're sampling. For people in simulation and statistics, it's like sampling from the empirical distribution you can think of. So now, outline of the rest of the talk. I will take care of the rest of this first bullet, the overview of simulation, including a little more technical details and stochastic gradients, and then just a couple slides on ranking and statistical ranking and selection. And then Ijo will present the meat of the talk, neural networks and learning, some new learning algorithms in the past couple years, and then some deep reinforcement learning application, including AlphaGo and Monte Carlo tree search, fully sequential statistical ranking and selection, and then back to the first motivating example I presented on the multi-echelon inventory management. Questions are welcome even during the talk, especially if something's not clear. Okay. So to kind of start the setting, the objective is the simulation optimization problem setting is written in this form. Here I'm just writing it as a minimization problem of an expected value of an output random variable L, and theta is the parameters, the decision, you can think of as the decision variables. Capital theta is the feasible region, and omega just represents a point in the probability space, because this is a stochastic optimization. And the assumption is there's no analytical form for the expectation. So the big question in simulation optimization is how to efficiently combine simulating, so you have computations that you have to exert to get more samples of, more omegas from this space, the L, to get L, and also to do a search, so you have to trade off between these two computational requirements. So some examples, common examples, queuing systems, waiting time is output that people are often interested in. The optimization is how you, for example, schedule servers in a network to reduce the average expected waiting time or average waiting time. Inventory system I introduced earlier. You're interested in the on-hand inventory, backlog, or lost sales in, for example, supply chain networks. And as introduced earlier, the optimization has to do with, for example, setting, this is traditional OR ways, setting, for example, base stock levels or reorder point, order up 2 levels to reduce the cost. And then in the neural network setting, as I mentioned earlier, we have this is just one neuron where we have inputs going into with synaptic weights, and then there's a function that basically transforms it, sums it, and then transforms it, and then this is just one point of these into the next layer of the neural network. And then, as he said, you have a loss function on the real data versus what the neural network is trying to approximate, and then you want to tune this vector parameters, which would be all these weights at each of the levels in order to minimize this loss function. Okay, so now a little bit more technical detail. So in the machine learning community, they usually call this a stochastic gradient descent, so you hear SGD all the time. In the traditional stochastic optimization and statistics community, it's one form of stochastic approximation, just finding the zero of the gradient. So, but basically it's a search on, with the gradient here, a step size multiplier, and recall that theta is the decision variable. So the important part of this is that we have to have a good stochastic gradient estimator. So traditionally in AI/ML applications, many of the applications, this part is actually what I call the easy part, because you have the form of the loss function, and you oftentimes they choose forms of the activation function that are easy to deal with. So calculating this is kind of the easy part of that. Whereas in sort of the traditional OR literature, this is actually usually the hard part. So that's why oftentimes people resort to finite differences. But a large community has worked with trying to come up with what we call direct and single run gradient estimates. So direct gradient estimates are ones that actually estimate the gradient, usually unbiased or sometimes just consistently, as opposed to finite differences, which always have a bias, although the bias does disappear as the difference goes to zero. But in single run is that you only need to do one simulation. The usual finite difference requires, if you do 4 differences, it will be d plus 1 simulations, where d is the dimension, or then the size of the vector, the parameter vector, or number of decision variables. So in the direct gradient single run, you would just do one simulation, and you would get the gradient in the same simulation as estimating the performance itself. Okay, so now we get a little bit technical. So 2 of the most straightforward ways of doing stochastic gradients are called infinitesimal perturbation analysis, or IPA. There are other terms that are used in other areas. So in finance, they oftentimes call it the pathwise method. In certain applications in computer science, they will just call it automatic differentiation. But the idea is that you're basically differentiating the sample performance itself directly. So recall this was our output performance. This is gradient with respect to theta. If we think that theta appears directly in the output performance, and if we can justify this exchange of gradient and integral, then you just take this inside, and this red part is your stochastic gradient. Okay, so then if this interchange is justified, then you will have an unbiased estimator. In many applications, this is not justified, so we'll talk about that a little bit later. So for a stochastic model of this form, so we write this theta and omega as kind of abstract, but if we want to write it as, in this case, we'll use p. P is a function of random variables, x's. This is another vector that's a function of the underlying uniform random numbers that generate the simulation. And then theta can appear also in the function itself. Then if you do that and you do the differentiation, you get a form that has two terms, which has to do with the sort of sample gradient directly here, and then the part that that appears in P directly. Oh, sorry, that's the part that appears in P directly. This gradient should be kind of operator on the second argument. This is the chain rule here that's applied. Okay, and so with that, you can get a estimator that if, as you said, certain conditions on, in this case, P are satisfied, then you get an unbiased estimator. And then if you look at this equation here, you might ask, well, what is this thing here? It's a derivative of a random variable. Well, it turns out that you can express this in terms of the distribution function and density of the input random variable. So there's a nice formula for that. And it's even nicer in certain cases where the parameters of interest are things like location and scale parameters. Okay, so that's IPA. Here's just a quick example of it. If the random variable is like exponential random variable with mean theta, then those of you who know simulation know that one way you can generate that is just by taking the mean, multiplying by the negative log of the u as a uniform 0, 1 random number, then taking the derivative of this, you can see here it just turns out to be minus log of u. So that's a way of getting the derivative of such a random variable. For a single server queuing system, first come, first served should be there. There's something called the Linley equation for the waiting time. It turns out you can just differentiate that nicely and get a nice form of that. So in this case, this is kind of like the automatic differentiation rule. Okay, so to show, well, this is probably hard to see right away, but so it turns out that if you're going to try to apply IPA to an SS inventory system, and the two parameters are little s and big S, little s is the reorder point, big S is the order up to point, then if you keep big S constant and you change little s, it turns out you can compute the sample path derivative, and it is unbiased. However, if you keep little s constant and increase big S, it turns out that the IPA estimator is biased, okay, because if you could write out the dynamics for the sample path, you would see there's a discontinuity as you increase the value of big S. So before I talk about some ways to take it to come up with estimators in those situations, I'll quickly go through the other method, the likelihood ratio method, in which case, if you recall before, I put the theta inside the p. If we say p does not depend on theta, but we put theta inside the distribution, this is the input distribution function, then when if again we need this ability to interchange expectation and derivative, then you end up taking a derivative of the log of this, again, this f little x is the density of the input random variable, and after, very simple algebra, you get this expression, which basically says, if you do a simulation and you estimate, for example, this is, say it's waiting time, if you take that waiting time and you multiply this by this derivative of the log of the input distribution, you get an estimate for the gradient. So again, in the same run that you do the simulation for estimating waiting time, you get a derivative for the estimate of the derivative of waiting time with respect to a parameter. And just like we did for the exponential distribution for IPA, there's also an easy form to find out what the derivative of that of the distribution in this case is for an exponential distribution. Okay, so this thing, if this for example, just x itself, then you would just have to multiply x by this quantity for every time you have an output x. But of course, as I said before, L is usually a more complicated estimate. Okay, I think I'm going way over time here, but so the likelihood ratio, this is when you have n components in the input. If they're independent, then you get, it's the product of the marginals, so you end up getting a sum of these derivatives of logs. If it's Markovian, so this, like the xi represents a Markov chain, and this is the transition density, then you get this kind of sum. It's a sum also of derivatives of log, but now you have the one-step transition densities. Okay, so I mentioned earlier this discontinuity issue in gradient estimation. There are ways to overcome that. One is called smooth perturbation analysis, and another one is called generalized likelihood ratio. And since I'm over time, I won't actually try to go through this example. Okay, so before I hand it over to EJ, I will talk just very quickly about ranking and selection, just to give the setting because he's going to build on this. So typical statistical ranking and selection scenario is you have, in this case, k different alternatives that you want to choose from, and they have unknown mean performance, and you want to try to estimate the one that is the best. In this case, we will assume that the best is the largest. Is that right? Yeah, the best is the largest. Is that right? Smallest. Oh, smallest. Okay, I can't tell by this here. Okay, smallest here. So we want to choose the first one in this case without loss of generality. We ordered it 1 through k. And what you do is you have a simulator and you're simulating estimates of these alternatives, and you want to kind of maximize this idea of probability correct selection, which is that the sample means are giving you the true best. In this case, the sample mean of the first would be the lowest of the ones that are actually simulated. Okay, so the main idea I want to talk about here is this idea of the optimal computing budget allocation, which Professor Chen was the kind of founders of this technique and approach, which has been used a lot in simulation. And so all I'll do is give you kind of the punchline of this. And so the punchline is that in order to try to maximize this probability of correct selection asymptotically, it turns out that you have a very easy, intuitive explanation of how you should allocate simulations, at least asymptotically, which is if this is the alternative I to j, this ratio shows that it should be proportional to the variance. So if you have an alternative that has, you don't know much of, then you should simulate it more. And then it should be inversely proportional to the difference between the system and what you think is, or what you know is the best. So this delta I is the difference from the best. So if it's close to the best, then you want to allocate more simulations because you think, it might be the best. If it's far away from the best, then you shouldn't do that. Okay, so I will stop here and let EJ.
Okay, thank Michael, thank you, the chair and all the audience here. So I'll present the rest of the stuff. I try to help people understand that there is a strong connection between AI and simulation, but I also hope you can see the difference. So first, the neural network and learning. So the neural network is a general function approximator and also serves as the basic infrastructure of the AI. So for the neural network, there is an input, like for image classification. So the input is basically a huge vector of pixels. So the input data is randomly drawn from data sets like image nets. So this recursion is called the forward propagation of a neural network. So we can see that the input is in each neuron, so is also a vector. And each element of the vector is multiplied with the synaptic weights. So that's the parameter we want to tune. And then the summation is sent to an activation function, which is nonlinear. And then a scalar is delivered to the next layer of neurons. There are many layers of neurons. So this is a basic structure called a multi-layer perceptron. They are more complicated structures of the neural network. But the computation in the neural is basically a composition of linear and nonlinear. So then deep learning. So the deep learning is essentially a simulation optimization problems. So I use this again the image classification as an example. That ON there is called labels. So which is a vector. So like if I take the image 0 as an example, so the vector is represented. The first element in that vector is 1, and the other elements are 0. That's a representation of the label. The PI there is called the softmax. So we transfer the output of neural network into a probability, and this loss function is called cross entropy. So it's used often for classification. That's the objective for training a neural network is basically to tune the parameters, every synaptic weights in the neural network, to minimize that expected loss. Because the input of the data is randomly sampled from data sets, so the output of the neural network is also random, and also there are other sources of randomness, such as the dropout, which randomly sets some synaptic weights to be 0, and also like reshuffling in the gradient descent. So it's like basically a simulation optimization problems. But this simulation optimization problems has a huge the dimension is usually very huge. Like for the GPT 3.5, the number of parameters is 175 billions. So and also for the objective, the new in that objective often has many local minimals. So for optimization problem with this complexity, the stochastic gradient, or gradient-based stochastic optimization is often the only feasible path. So this SGD is a basic algorithms. So the key here is how to have this unbounded stochastic gradient estimator, this G. Also, there are other better optimizer than the SGD, such as the Adden-Gray, Adden, but they are all like a gradient-based stochastic optimization methods. So the most important stochastic gradient estimation methods for training a neural network is this backpropagation algorithm. So it was originally proposed by Geoffrey Hinton, a Turing Prize laureate, in this paper published in Nature in 1986. So this algorithm has been embedded in almost every like a machine learning platform, such as PyTorch, TensorFlow, etc. So this is the derivative estimates for the J synaptic weights in the ice neurons of the else layers corresponding to the nth input data. So here we can see there is okay, you cannot see the arrow there. So at the end we have a residual arrow at the end. So that the derivative on the right hand side. That residual arrow is propagated backward by this recursive equation through the neural network. So we can see that in this gradient estimates, the delta, which is computed by the backward propagation, and the x, which is the signal computed by the forward propagation, they are separated in that gradient estimates. So, so for the BP, one forward propagation and one backward propagation are sufficient for computing the derivative with respect to all parameters. So that's very efficient. As I said, there are numerous parameters in the neural network. So that's the reason why it has been embedded in almost every machine learning platform. For BP, the loss function and the activation function requires to be differentiable. Also, there is a subtle issue here. So you can see that in that recursion. So the derivative of the activation function is differentiated, and then also it is multiplied repeatedly in that recursion. So this is a derivative of activation functions called sigmoid. So we can see that it has a peak at the center and decays to 0 fast at the tails. So if you multiply that repeatedly, so it's very likely to end up with a very small number or a very large number. So then on many sample paths, the parameters either doesn't update at all or like change dramatically in some other sample paths. So this is called the gradient vanishing and explosion issue. So like our work, we show that the BP is essentially a pathwise derivative estimates, or IPA, just Michael talked about. And also under certain condition, it can be proved to be unbiased. So also the BP, this is the complexity of the BP. So it's m squared times the L. The m is the number of neurons in each layers, and the L is the number of layers. However, if we don't use the backpropagation, then to calculate the pathwise derivative estimates, the complexity would be higher. So this matters a lot if the neural network is large. So then reinforced learning. So the underlying mathematical model of the reinforced learning is Markov decision process. So it starts from an initial state, and then an action is determined by a distribution, pi. Then reward is collected. And then a new state is determined by a transition probability p. So this is essentially MDP. It's a very classical area in AOR. So what differentiates the traditional methods for solving MDP from the reinforced learning is actually simulation. So, so in the RL context, so the transition of the state is usually very complicated. So that P you usually won't have analytical forms, but we can still simulate it. Sometimes we don't even have the analytical form of the rewards, but we can also simulate it. The objective is to maximize the expected rewards, and in RL, so it's based on the simulated sample paths of the states and the rewards for optimizing the policy. So that's RL. So the deep reinforcement learning is what really made a game change. So it's it's under almost all recent breakthrough in AI, such as the AlphaGo, ChatGPT, etc. So the objective is to maximize the expected rewards over that policy functions. So this is a complicated functional optimization. So the policy gradient is an important branch of DRL algorithm. So basically, it parameterizes the action policy by a neural network, and then the action is taken based on this the policy given by a neural network. So after doing this, so a complicated functional optimization becomes a parametric optimization. So however, to ensure that the neural network has sufficient capability on approximation, so the number of parameters in the neural network is required to be usually very large. So to solve such a complicated optimization problem, again, the only feasible path is still the gradient-based stochastic optimization methods. So this is a very classical, DRL policy gradient methods is called the reinforce. So, so this GT is called the rewards to go from T to capital T. I will explain in detail that the searching direction is just the likelihood ratio estimator. So, so on the first line, that's the classical likelihood ratio estimator. So because the expectation is additive, so we can interchange the order of the summation and take the summation out of the expectation. So then we can see that the summation on the second line is separated into two parts. The first part is independent of the action AT, and the other parts, that is the rewards to go, it depends on action AT. So the proof for justifying that the first part can be removed from the expectation is given as follows. So the estimator inside of the expectation is just the searching direction in the reinforce algorithms. So I'll use that picture on the right-hand side to illustrate a subtle issue. So in the reinforcement learning context, it's usually very expensive to simulate a trajectory in the episodes. So it's inefficient to use the original form of the LR estimator to update the parameter once based on the whole trajectory of the data. So instead, the trick to increasing the data efficiency is to update the parameters at the intermediate steps. At the intermediate steps in the whole trajectory. So that's the reason why we use the likelihood ratio estimator in the form in the last line. That's the searching direction in the reinforce. However, we may have noticed that the parameters keeps updating, while the data for computing the gradient estimates is generated by the parameters at the beginning of the episodes. So the reinforce works, but it's not the most powerful one. So this proximal policy optimization, PPO, is one of the state-of-art DRL algorithm. So, so there are a lot of details. I will skip many. So basically, it is derived following these 3 steps. First, we add a baseline, which is a new network, a well-trained neural network, and for estimating the conditional expectation. The multiplication of the likelihood ratio and the baseline can be viewed as a control variable, which has 0 mean, but reduces the variance. And then we implement the importance sampling, which changes the probability measure to so that the data can be viewed as if it is generated by updated parameters, even though the parameter is kept fixed at the beginning of the episodes. So the updated parameters may move far away from the initial parameters, so that the importance function may introduce a large variance. So then the third point is to clip that ratio to avoid the variance issue. So I won't talk too much about details, but the essence of the PPO centers around allowing the multiple updates in one episode by following these 3 steps. So then I introduce several new learning algorithms. So as I said, the BP is essentially password derivative estimates, that is IPA. So as a simulation guy, so what naturally comes to my mind is why not likelihood ratio methods. So likelihood ratio methods, as Michael just explained, it takes differentiation on the density. So it's difficult to push all the parameters in the new network with many layers of nonlinear operations into the density. So what we can do is we artificially inject additional noise to each neuron, so which will significantly reduce the computational difficulties. So this is the LR estimator. So it looks very simple. So that's the loss function. It is multiplied by the weight function, which is given as a product of the signal and the likelihood ratio of the injected the density of the injected noise. So for the LR, one forward propagation is sufficient for computing the derivative with all parameters. It has a simpler form, and it don't have the propagation of error anymore. It can have these discontinuous loss and activation functions, no gradient vanishing or expulsion issue anymore. So that's a discontinuous and activation function. So the LR can also be proved to be unbiased under certain conditions. The LR has the same complexity as BP, but it's much faster because of the simpler form and the no backward propagation of the error. And also, for the higher order gradient estimates, which is difficult to compute it by BP, LR can handle it very easily. So the LR has been extended to more complicated neural network structures, such as convolutional neural network, recurrent neural network, graph neural network, spiky neural network. So BP is generally simple. The LR is generally simple than BP. So take this RN, for example, we can see how big the difference is. So the computational flow of BP is on the right-hand side. So the residual error need to a flow backward throughout the time. So the vanishing gradient issue is even worse, and also it cannot process the input series in parallel, which is the major reason why RNN loses steam after the invention of the transformer, the backbone network of ChatGPT. So then that is on the left-hand side is the computational flow of the LR. So we can see how simple it is. No backpropagation of the error throughout the time, and also it can be easily parallelized. So LR usually has larger variance than the password gradient, that is IPA. But we also have many variance reduction for reducing the variance. So not only this narrow-wise noise injection can reduce the variance, it also allows parallel computing. And the antistatic variance can reduce the variance using two negatively correlated random variables with the standard expectation, and also causing Monte Carlo can be used. So here are some numerical results for comparing the LR with the BP and another method called ES, which does not use the backpropagation as well, but it doesn't really perform well, so I won't talk much about it. So there are 4 types of neural network and 4 types of data sets. So the accuracy is the accuracy results is shown on both the benign data and the adversary data. So this is called the adversary phenomenon. So a neural network, a well-trained neural network can have high accuracy for classification on the original data, benign data, but the accuracy would drop dramatically after these adversary attacks, which are very small perturbations generated by an algorithm. So that's that phenomenon has been known in AI society. Basically, the LR is the accuracy of LR is comparable to BP on benign data, but the LR performs much better on the adversary data than BP. Also, on the right-hand side, you see there is a spiky neural network. So a spiky neural network has discontinuous activation functions. So BP cannot handle this continuous activation function. So that BP is actually a modification of the BP. So we can see that the accuracy drops a lot on the adversary data, but the LR, the neural network trained by LR, is extremely robust in the adversary data. So and also, as I said, the reinforcement learning is to maximize the expectation of cumulative rewards. Then the question is, why maximizing expectation? First, maximizing expectation is relatively easy. Because the expectation is additive, so there is a Bellman equation, which serves as the foundation for many reinforcement learning techniques. Second, maximizing expectation is usually sufficient for classical reinforcement learning problems. So these are 2 classic problems. So we can see that in these 2 examples, given the action and the state, the transition is actually deterministic. The probability model is only used for capture the complexity of the state transition. And also the rewards are designed to be deterministic. So you can see on this, this is a picture showing the rewards and the variance. So a well-trained neural network would lead to a nearly deterministic cumulative rewards. So there are no variance anymore. So, but this is the application in the business. The situation is very different. Like in the output of business system is usually contains the lot of randomness. Like take the inventory as an example. So the demands and the lead time, these are all randoms, and this randomness is generated by the group behavior of humans, and which is very hard to predict. So then it's reasonable to ask whether we can it's better to use the other performance measure. So the quantile is an important risk measures that can capture the tail behavior of distributions, but we also know that it's notoriously difficult to optimize. So this K-Wolf's type SGD works like for any stochastic optimization problems with any measures. but it works only for relatively low dimension optimization. So, so the quantile is essentially, for the continuous distribution, essentially the inverse of the distribution functions. So we can express the gradient of the quantile as this ratio. So it's a ratio of two, a ratio of the gradients of the distribution functions evaluated at the quantile value itself. So then there is a discontinuity issue for estimating the density and the denominators. In the first paper, at least, actually there is a GR estimator for estimating for giving the unbounded density estimator, but it requires twice differentiability on the rewards function if I want to apply it in the RL context. But in the RL, the rewards function don't even have any degree form usually, so it's difficult to have unbounded gradient estimator. And also, there is no single round unbounded gradient estimator for the quantile. It usually requires many numbers of simulations for estimating the gradients. So in the second paper, we actually established a central limit theory for that gradient estimators as the sample size goes to infinity. But I will explain that in the RL context, there's a central limit. The limit series isn't really relevant. So for the quantile-based reinforced learning, so there is no Bellman equation. So many mean-based, the reinforced learning methods based on the Bellman equation cannot be applied. The policy gradient is still well past. There is this difficulty for estimating the density, but we don't. So the gradients, so the density in the gradients is essentially a positive scalar. So we get rid of the density. It's still the direction of the gradients. So we just use that direction. As I said, it's usually very expensive to simulate a trajectory in episodes of the reinforced learning. So it's computationally infeasible to use many samples in the whole trajectory for estimating the gradients and then update the parameters for once. So then we propose this quantile-based policy gradients, QPA. It's a two-scaled stochastic approximation. So it allows to update the parameter once after one episode of simulations. So this coupled SGD tracks the coupled ODE. The first iterations tracks the quantile given fixed parameters. The second ODE tracks the stationary point of the gradients. Because the learning rates goes to 0 in a higher order. So in the second iteration, the learning rates goes to 0 in a higher order. So the first iterations converges much faster. So when in a symptotic analysis, we can view the parameters as being fixed, actually. So it also admits the central limit theory and has mean square error as shown as follows. So we can see that the cumulative rewards is embedded in an indicator, so it cannot be decoupled. So unlike in the reinforce, the rewards to go is used to compute the gradient estimates. Here, we need to use the data in the whole trajectory to compute the gradient estimates for updating the parameters. So as I said in the mean-based reinforced learning, deep reinforced learning, so updating parameter once in one episode is insufficient for complicated reinforced learning problems. So again, a lot of details. So I basically use these 3 steps to analogous to the PPO, analogous to those in PPO, to improve the data efficiency. So first, not only we keep track of the quantile at the end of an episode, we also keep track of the quantile of the cumulative rewards at different lengths, with different lengths. So we randomly draw lengths, and then the quantile of the cumulative rewards with that length is updated. So these two coupled SGD solves a changed optimization problem. So on the fourth line. So it's a different, it's a summation, it's an average of the quantiles of the cumulative rewards with a length ranging from T0 to T. And also we can show that the difference between these two optimizations becomes negligible as the T goes to infinity, given bounded or stepped Gaussian rewards. Then again, we implemented the importance sampling to allow multiple updates of the parameters in a single trajectory of the simulations. And the CLEAP operation is introduced to deal with the variance issue to have this quantile-based proximal policy optimization, QPPO. So here, I use this picture to make a contrast between the QPO and the QPPO. So in the QPO, so it has it used the Intel the data in the Intel trajectory for updating the gradient and the quantile and the gradient estimates, and then update the parameters for once. So in the QPO, a subsequence of the trajectory with the length randomly given by a randomly drawn length is used for updating the quantile and gradient estimates. And then the parameter is multiplied multiple times before the next episode of the simulation is run, and then the parameter is updated to the latest one. So that's the difference. So we can see a numerical experiment. So this is a simple one. So the vector is contains these three elements. At each step, the elements components in the elements are reshuffled. So their orders will appear randomly. Then the rewards is given by this uniform random variables with the length of the support determined by the number we picked, the elements we picked. So this for the reward has a zero mean. So if we apply the mean-based reinforcement learning, like a PPO or reinforce, they cannot learn anything. But for the quantile, we know that the optimal action is to pick the smallest elements. So like the QPO, the QPPO, so they are quantile-based reinforcement learning. So we can see that the quantile value increases. Because of the high data efficiency, we can see that the quantile value, the quantile value of QPPO increases fast and it reaches a higher level. And also it can makes 100% correct decisions after a few iterations of learning. But the QPO, it can only reaches like 80% of the correct selection, till its convergence. The SPSA is a Keith-Wolfe style type of SGD, so it always works. But even for these simple problems, it cannot work as well as the QPO. Finance examples. So I may skip this one to save some time. So basically, the QPPO can give you a better hedged portfolio than the PPO. I then talk about the connection between ranking selection and the AI. So first, the Monte Carlo tree search. So in the Monte Carlo tree search, so it's a general dynamic decision framework used often in machine learning. So at each of the nodes, the tree is searched by simulations, and following these 4 steps. So at the selection stage, so this is showing the first pictures. This is the selection stage. So the tree policy determines the allocation of simulation replications sequentially. Based on the sample information of the node in the sample information of the tree nodes, which have already been explored. Then at the expansion stage, so a new nodes which hasn't been explored is added to the tree. And at the simulation stage, a base policy is used to determine the simulation replications to form a simulation path from the new nodes to end leaf nodes, where the win or loss will be obtained. And at the last stage, the backward propagation stage, the number of simulations and the number of wins and losses will be updated from the new nodes to the root nodes at the very beginning. So these are 4 steps. So the in the machine learning society, the upper confidence bounds for tree, UCT, is a popular tree selection policy. So it balances the exploitation and exploration. So actually, this is also the principle in the ranking selection. So then I claim that the ranking selection can serve as a tree policy as well. And the recent research shows that the OCBA and the AOAP can achieve even better performance in the Monte Carlo tree search. So, so AI has fundamentally reshaped the many areas since these sensational events when the AlphaGo topped the best human players. But how? So the recipe is basically these three bullet points. First, Monte Carlo tree search. Second, to neural network. Third, UCT node selection policy. Because the tree is huge, a policy network is used to guide the sample, the searching. So in the pictures, the tree, and also a value network is used to decrease the depth of the searching. So the 2 neural networks are trained first by deep learning before the Monte Carlo tree search, and then first by reinforced learning before the Monte Carlo tree search, and then by deep learning after the Monte Carlo tree search. So I won't get into too much details. And then we can see that the policy, this is the UCT. So the information of the policy network is added to the prior information P in that U function, which encourages the exploration. And the value network, the information of the value network is added to that Q, which is the state action value function. So this work formulates the node selection problem in MCTS as a multi-stage ranking selection problems, and extends the an AOAP algorithm, which were originally designed for one stage ranking selection, to a multi-stage ranking selection, creating a AOAP for tree. We call it AOAT. So we then use 2 neural networks to improve the performance. And we show that the AOAT can beat the UCT used in the AlphaGo 0 and mu0 in 3 examples. So this is a tic-tac-toe examples. So we can see that, so because there is a 5 minutes, 10 minutes, okay. So there is a tuning parameters in both the AOAT and UCT. So we tested the performance of several parameters, and we presented the best and the worst. And so the AOAT Gaussian is derived assuming the Gaussian sampling distributions, and the AOAT Bernoulli is derived assuming the Bernoulli sampling distributions. So we can see that when the AOAT Gaussian plays against the UCT, the worst case can even beat the UCT, the best case of the UCT. And for the in the downsides, the AOAT and also the AOAT Bernoulli, the AOAT Bernoulli, the best case of the AOAT Bernoulli, and also the best case of the AOAT pi. Oh, the AOAT pi uses so the AOAT there only uses the value network, but the AOAT pi uses both the value network and the policy network. So then the AOAT Bernoulli and the best case of AOAT Bernoulli and AOAT pi can beat the UCT. So we can see on the right on the right side. So we can see that the tree searched by the UCT, AOAT, it's expanded more even than that searched by the UCT. That indicates that better exploration and exploitation. And also on the downside, so we can see that it takes the new network. This shows the winning rates between the when the AOAT plays against the UCT as with the increase of the iterations in trainings. So that basically says that it takes the new network in the AOAT should be trained better than that in the UCT for achieving higher winning rates. So here, this is the more complicated examples. I may skip it. So this is a 5 in a row again. So the border is 10 by 10. So the real goal border is 19 by 90. So we don't have a supercomputer, but we can still have good performance in this 10 by 10 5 in a row again. So then I talk about the ranking section. We visit the ranking section. So from a fully sequential perspective, so the dynamic sampling decision can be formulated as a stochastic dynamic programming, and this allocation policy it allocates the simulation replication sequentially. So the AT allocates the T simulation replications based on the information collected so far, sample information collected so far. And the selection policy makes the final selection at the end based on all the sample information. And the Bayesian framework is introduced. The AOAP I just talked about is derived in the stochastic dynamic programming framework. It's myopic sampling procedures, but it can be proved to achieve the symptotic optimal sampling ratio. So I will skip many details, the technical details. This work, it unifies in the ranking section, there is called a fixed precision and a fixed budget, two branches. So this work unifies these two branches and consider general sampling distributions. In the ranking section, usually people consider normal sampling distributions. And then the fixed budget problem is formulated as the finite horizon MDP. The fixed precision problem is formulated as infinite horizon MDP with a stopping time. And also a DRL-based ranking section algorithm called alpha rank can combine the classical ranking section algorithms and significantly improve their performance. And a general parallel computing framework can be integrated with alpha rank for solving large-scale ranking sections. Okay, through the analysis of the behavior of the AI behavior, we can also the new insights on how to design a well-performed ranking section algorithms can also be reviewed. So traditional wisdom relies on the mean variance trade-off. Here, we also emphasize the importance of the trade-off between mean variance and induced correlation. The induced correlation has been neglected in the classical ranking section procedures. So here is the rollout policy. So it's basically used in Monte Carlo tree search to learn that PCS, or the state value action, the state value function Q. The base policy used in the rollout, the more accurate the function Q could be estimated. So then we use the classical ranking section as the base policy. So again, then we use the rollout, but we train a new network to create the alpha rank. So so here, so we first roll out, and then we collect the samples of the estimates of the function Q, and then we use it to train a policy network by deep learning. Then we can use the alpha rank to solve the fixed budget ranking section problems. Also, we can use a well-trained value network to make decision, make the stopping time, the decision of stopping when the PCS guarantee can be the guarantee of the PCS is reached. So that's how we unify these two framework. So, because I'm running out of time, so basically what I want to show is that here is we have a lot of experiments. So that's the first picture. So we show a very classical ranking section problems. We can see that the rollout policy performs much better than the classical ranking section procedures. And the second picture, you can see that the classical ranking section even decreases the PCS when more simulation replications are allocated. So it's completely make a decision in the wrong way. But the rollout methods can still increase the PCS. And also in the ranking section society, we always assume the normal sampling distribution and the conjugacy priors. Here we remove the conjugacy assumptions and use the particle filtering to update the posterior approximately, and then we can see the rollout policy plays well again. And also then this alpha rank. So the alpha rank, after some training, it can surpasses the classical ranking section procedure that's on the right-hand side. And also it can be integrated with that DCR framework to solve large-scale ranking section problems. Like here we can say solve like 10,000 ranking section problems with 10,000 alternatives. Typically in the classical ranking section literature, it's like there are only like hundreds or something. Yeah, also we solve the general sampling distributions gamma. Usually this is rare in literature, so usually the normal assumption will be assumed. And also we can like do this the fixed precision, the guarantee. So the Reinhardt is a two-stage indifferent zone methods. The KG is a sequential indifferent zone methods. So we can see both KG and Reinhardt, they wasted too much of the simulation replications to guarantee the PCS. We can see that their final PCS they are way above the targets. The target is 0.5 and 0.9 and 0.95. But the alpha rank, they consume much less simulation replications, and the PCS is very close to the targets. And this is try to help people understand why the alpha rank can do better. So because the classical ranking system missed some information, important information that the classical ranking system procedures neglected is the induced correlation. So then I try to use this picture to show that how the alpha rank better use this information to achieve better performance. And then inventory simulations. So the inventory control is actually is a multi-period news vendor problems. And to find the optimal policy is to solve a stochastic dynamic programming or MDP. Okay, so then many of the researchers emphasizes on how to get simple like a form of the optimal policy, such as Stoch SS Michael just introduced. But those policies are derived under very strong assumptions, like a single echelon, backlog, IID demands, which are rarely satisfied in the practice. So I've been working together with Jingdong.com, that's one of the largest online commercial companies in China. I guess it's also the largest around the world. So, so it has 10 million products. And it has multi-echelon lost sale, dual sourcing, non-station demands. These are all found in the real problems. There is a network of a warehouse to fasten the delivery to the customers. So that's the warehouses. So the central warehouse has large can store more products, but they are far away from the customer. The mini warehouse, they have a limited space, but they are close to the customer. Actually, it's, the literature studying the multi-echelon warehouse network is really rare. So then we can use the AI techniques. So here we propose two. One is called deep learning methods. Another is the deep reinforcement methods. Both of them beats the classical like a base stock policy. So also you can see the number of products is large, like more than 10,000 products. And also in the warehouse examples, mini warehouse examples, there are 1,000 products. And also we can apply the quantile-based deep reinforcement learning methods to this 3-echelon inventory system in a series plan chain. And we can see that the quantile is higher, and also the QPO, the rewards of the rewards is more concentrated on the center. So that means the decision is more risk averse. And also we can see the behavior of the decisions trained by this QPO. We can see that the ordering decisions are much more stable than that obtained by the by PPO. So that means this order decision will be more receptive in practice. Okay, that's all. Thanks.
Somebody has, we'll have time for maybe one question. We are a little bit over time.
One thing that you seem to don't talk too much about is if these gradients don't exist, because some of these involve, discontinuous activation function, then, it's not necessarily a differentiable function. How do you handle that?
So you mean the activation function, right? If it's not differentiable. So here, I in this slide, in this talk, I showed an alternative way for estimating the gradients, which doesn't require the activation function to be differentiable. So that's the ratio methods. So in the simulation area, we have two well-known gradient estimation techniques. One is called the IPA, that's pathwise derivative. If we use that, it requires the activation function to be differentiable in the neural network. And the Lagrange methods, because it differentiates the parameters in the on the density, so it does not require the activation functions to be differentiable. So one thing to be noticed that is I injected some artificial noise into the neuron to allow the differentiation on the density. So does that answer your question? Okay, thanks.
Since we're out of time, we can thank our speakers for the tutorials. Thank you.